All right, so the first thing is the format on the homework. Start paying attention to this a little bit. A few things, your name, the date, problem number, and the page number. Now, the idea here is to create an independent set of work that someone can look at 10 years from now and know what you were doing, because when you're doing engineering work, that can happen. People need to look at the paper and understand what's happening there. So what that requires is a problem statement to tell what's happening, what the question is, what you're trying to answer. Now, that doesn't have to be copied out of the packet. It can be paraphrased, but there needs to be something there, okay? That also requires a sketch. What the type of engineering we do is very visual, so we need a sketch of what's happening there. If we don't have that, people don't really understand what's going on. That's part of the problem statement. Then we need to go through the work in a sort of a logical way, step by step, so someone can just follow it down. And then at the very end, I want all the answers to one problem in a box. Okay? And it's important that someone can see what the question is, see the picture, and follow your work. That's what's important. It's also important that it look as professional as you can make it, because, as I've mentioned, that's an expectation in this career. When you start working, if you work as a consultant, you're going to be billed out for $100 an hour in current wages, okay? And that's or not wages, but bill. You're not going to see $100 an hour, but your company will bill you out at that. Now, so there's expectations for that, and I just want to impress on everybody. So everybody just look at your work and see if you meet that criteria, okay? Do you have the information on the top? Do you have a clear problem statement and a logical place for it? Do you have a sketch and a logical place for it? Can someone just follow your work through in a real step-by-step logical way? Could someone do that? These are important parts of, okay, and then have you put the answer in a clear place with a box around it, okay? That's the things that I'm looking for. And you're starting off here, you haven't done a whole lot of engineering classes, but I really do want you to start to develop those skills. When I went through the grading, and this is not atypical, but the work can be somewhat scattered. It's all over the place. And see, that's not how engineers do work. Engineers do work step, 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 answer, okay? And the reason is someone else can follow it then. It also cuts down on your errors. Okay, a straight edge is a good idea. We don't need to make beautiful sketches, but I just use an old library card, okay? Nice straight edge, cleans it up a little bit, makes it look more professional, okay? Staple the problems in order. There were a number of these that were stapled out of order, okay? That's not how you present work to someone, okay? And the point I'm trying to get across here is you're not just doing the work, you're presenting it, okay? You got to kind of turn it around and look at it from my point of view. And eventually that's going to be your client's point of view, who's paying you $100 an hour, okay? That's what I'm trying to get across here, and what I want you to start working on. And I'll be frank, I'm not seeing that on some of the papers that are turned in. They're a little scattered, they're hard to follow, et cetera, et cetera. Now, you got 3 years to work on this, okay, before you start working. But what I want to impress that upon you is that's an expectation here, okay? And just work on it. Every day, just get a little better at it. That's what I'd like to see, okay? You're learning statics here, but you're also learning some other things and some of these other skills I'd like you to work on too, okay? All right, so just give that some thought. Now, I didn't grade this for format, but in the future I will, okay? And these are some of the notes I might use. I don't like writing this stuff out every time because it takes me quite a while to do it. So SC means use a straight edge. One box means put all the answers to a problem in one box. Sketch means include a sketch. PS means problem statement. And can't read means I can't read your writing, okay? Now, not everyone has beautiful handwriting, I know that. But legibility is very important, okay? Again, I've done surveying work. I write stuff on stakes. If I write a 5 and it ends up looking kind of like an 8, that could be real problems, okay? Like very expensive, big problems if I do that. So legibility is important, okay? It's important that people can read your numbers, okay? All right, so that's the first thing I wanted to mention there. All right, let's look at some of these. Now, the other thing I want to mention is in the packet, the answers are next to a lot of the problems, or most all of them. There's a few that don't have answers, but I do give you the answers for most of them. And if you're not getting the answers that I'm getting there, you should ask yourself why, and then try and find that out, okay? Okay, so those answers are boxed in the packet, so look for those. And if you're not getting those, try and figure out why, okay? That's what I would suggest. So let's have a look at this, and if you have questions on any of this, let me know as we go through. And that's another little thing, you're paying me to do this, to teach you this stuff. So if you got questions, let me know. Let's see, what do we got?
I have a question about,
yeah.
This is probably overly specific, but if you give us graph paper, I put the graph paper on the back, even though that was the first problem.
Oh.
I wanted my name and everything up front.
Right.
Do you usually just the problems to be, you know what I'm saying? Because this is technically the first problem. I don't know.
Yeah, sometimes things get a little out of order because people want to go back to back, or maybe there's some things that might happen. That's okay.
Oh.
But some of the assignments are kind of random. They were just kind of put together.
I just didn't know if that was a big
And I get it. These days, I think it's important not to waste paper too. If you want to go back to back or something, that's cool. It's okay. But just something that's kind of logical, makes a bit of sense. Like this is what I'm looking for. Okay. Let's see. There we go. Okay, there's the first one right there. So on this one, there we go. Okay, that's what it should have looked like when you put the vectors 3 in a row. Some of you just didn't have the right angles on there. I mean, you should use a protractor and get the things written out at the proper angle there. And some of you had angles that were just incorrect. And the other thing is, I gave you a space to put the answer, and yet some of you were not filling that in. I mean, that's why that's there, see? And you kind of have to understand, it's kind of that professional presentation. I'm going through 36 of these things. I don't have time to waste time looking around pieces of paper. It doesn't sound like much, but when you multiply it by 36, it's very disruptive to my concentration, okay? I want this stuff laid out. I want the answers right where I can find them. I don't have energy to burn looking around for stuff. It's just, see, and that's kind of, again, that's that engineering thing. Logical, laid out in a clear way, okay? So if I got an answer space there, put the answer there and give me the answer. I didn't have some people just gave me a graph, okay? I'm not looking for a graph, I am, but I'm looking for the answer too, okay? So, and the other thing on this was these angles are measured with the horizontal. I think some of you might have been measuring, calling that angle 60. That isn't 60. 60 is with the horizontal. Right there. This angle isn't 75. 75 is with the horizontal. That's how that would have been laid out. That's how you would graphically work out vectors. Okay. So we got any questions on that one? Okay. And then the last resultant is right there. It goes from where you start to where you end. Okay. So that goes from the starting point, which is right here, if my pen will work, there we go, to the end right there. There's the resultant. Okay. Yes?
So my result, so it overlapped, and so, yeah. And so to find, would the angle be the angle inside?
Well, the angle, you can define the angle really however you wished. I mean, the resultant went like that, and I agree, this one was a little messy because there's an overlap there. It's kind of hard to read it. But the angle is always with the horizontal. I mean, that's how we reference angles. Mm-hmm. So if you're clear in the angle you measure and showing what line it's from, it should be fine if that answers your question.
Okay. So essentially you're putting a new x-axis at each.
Yeah, that's a good way to put it.
New x-axis.
Yeah, right.
Intercept point, new x-axis, and you're also measuring off of that.
Right, yeah, it's always off the x-axis, right? So you could think of
I said 2.3 centimeters, and you still said it was right, so it's like.
Yeah, there's a little bit of give and take on, especially on these graphical problems. I didn't expect the perfect answer, but I did expect something kind of in the ballpark.
Cool.
All right, we good with that? And you don't actually do work this way. I mean, but I just wanted graphically, this is what you're doing. When you're going through all that trig, that's what you're doing. You're just breaking everything up into X and Y components. You're doing this with it.
I heard the physics department had a race where they solved problems graphically and algebraically to see who could do it faster, and the graphically people won every time.
Did they? Okay. Yeah, I've seen elaborate.
It can be done graphically, it's always faster.
Yeah, and there were very elaborate graphical solutions back in the early 1900s because they didn't have all the computing power we have now. Yeah. But they're not used so much anymore. But they're, it's good to visualize. That's what we want to do here when we're working through stuff. Okay, the next one, the thing on this is to break everything up into components. All right, and then you just want to add everything up, okay? So there's that one, okay? So you just want to break up things into X components and Y components. I just use, you could use, use the 50-degree angle on the first one. Okay, or that's actually F2, I'm sorry. So 720 cosine 50 will get you the X component, and 720 sine 50 will get you the Y component. So that's, that's the approach on that one. All right, so what you're doing there is you're breaking this up into an X and a Y component like that. Now the one F1 should have a negative X component. If you look at that, you can see that. See, that's going to the left. So that's negative, and then you've got a positive Y going up. So that should be a negative X and a positive Y. And then you just add them up to get the resultant. You get the X and Y components of the resultant, okay? And then once you have that, you can take the square root of the sum of the squares, and that will get you the that'll get you the magnitude of the resultants. And then you can do the inverse cosine of Y over X. And that will allow you to find the angle. Now the angle on that comes, when you calculate it, comes out to be 79.2. But if you look at the components of the resultant, you've got a negative X and a positive Y. So that means that you're going to the left and up with those components there. So negative X and positive Y means to the left and up. Okay. I'm having some real problems running this thing. It doesn't seem to like PowerPoint in this mode at all. And once you've got that, then you've got negative X, positive Y. See, that means it's not actually 79.2, which would be down and to the right. Okay, these things can be 180 degrees off. So you need to have a look at them. And if they don't look right, you can add or subtract 180 to get the true answer. So the answer on this one, when you just run your calculator, comes out to be negative 79.2. But you need to adjust that because that's not the proper angle. It's actually up and to the left. So you add 180 to that and get 100.8. Okay. So any questions on that one? All right. Okay, the next one, what do we have there? We have to get the components of all three vectors for the next one. So I like to do these in tables. Just set up. So what we want to do is to find X and Y. And you have the different vectors there to do that with. So what have we got there for F1? We've got 240. Now that's 20 degrees. I'll use the cosine of 20. But I'll notice that that vector, what it does is it points to the left. So that'll be negative 240 cosine 20 for the X component. And then for the Y component, that'll be sine. So that'll be 240 times sine of 20. Okay. So I'll go ahead and do that. And that'll get me the two components for the first vector. So that's negative 226 for this one. Let's see here, let's get that a little bit stretched out here. So the first one, I had a negative on there because it's going to the left for the x component. The magnitude's 240, and I've got cosine 20. So what I'll get there is negative 226, roughly. And for the other, I'll get 240 times the sine of 20. And that will get me 82.1. I'll just call it 82. Okay, the next one there, F2, I've got up and right for this one. So that'll be both positive. So that'll be 280 cosine 60. And that'll be 140 positive. And then I've got 280 sine 60. And that will get me 243 roughly, positive. And then the last one there, I've got 460. Now that's down and to the right, so that'll be a positive x. 460 for right, and that's cosine of 75. And that's going to be 119. That'll be positive, and then I'll have minus 460. Sine 75. And that'll be a negative, and that'll be negative 444. Okay, like so. And then I've got them in columns there, so I can just add them up. And when I do that, for the x, I'll get roughly positive 34, and I'll get negative 120. So, if I want the resultant force, what I'll do is I'll take the 34 and square it, and take the negative 120 and square that. And what I'll get out of that is 124 newtons. And then to get that angle, I'll do the inverse tangent, arctan of y over x. So that's negative 120 over 34. And that comes out to be negative 74.3. Now that's below the x-axis, and I've got a negative y and a positive x. So that's going down like that, and so that angle there is 74.3 on that. Positive x, negative y. Okay. Any questions on that one? Okay, we're good. Okay. Then the last one, you've got the unit vectors for F1. You've also got the vector for F2. So what you would do on that would just be to use the trigonometry there and go ahead and work those two vectors out. You're going to deal with what we call direction cosines there. Let's see here. There we go. So there's F1 and F2. The one thing that might be a little bit confusing there is this one dimension, the 57 degrees is with the negative y-axis, excuse me, negative z-axis. Like so. To get the true gamma angle, which is the angle that the vector makes with the positive z-axis, you'd have to take 180 minus 57 and get 123. Okay, So when you get that second vector, you can easily either go 50 times cosine 46, which is alpha, cosine 62, which is the cosine of beta. And you can either do it two ways. You can go cosine 123, which is the gamma angle with the positive z-axis, or you can put the negative out in front and use the 57 that you're given. You can do it either way. Okay. All right, once you have both of those, you just add them up, get the total, take the square root of sum of the squares, you get the resultant. So we got any questions on that? Doing all right? Good. All right. All right, so that's just some little feedback on that, so we're good, okay? So do remember that format. I'll start grading you a bit on that. Now, you know, I don't expect you to spend hours working on this, but I do expect you to just slow down just a little bit and organize it and work on it for the next 3 years, you know? That way, when you start working, you'll have it pretty well figured out. Frankly, I didn't do the best job of this. I mean, one of the bosses I had when I started working, this was back in the days when people were quite so polite. He let me know that he didn't like the way my work looked, and I had to work on that pretty hard because he wasn't very happy with it. So I'm just trying to kind of get you all to work on that a bit now instead of later. Okay. All right. So we good? So we've got some more stuff due. You know, we always have stuff due, right? So we good? So okay. Now for the next one, this is 143. All right, so this is more of that 3D type stuff. So do we have any questions specifically on this one? We do have what we call a double projection in there.
Yeah, you do like cosine 72 cosine thing.
Yeah, right. Right, and the tip off, and I guess, you know, I don't quite know how to say this, but sometimes some people just have good visualization skills. They can just see this stuff on a flat piece of paper. Some people don't. I mean, you know, there's a range of people's kind of innate ability to do this stuff. So what I'm trying to do here is give you the cues, if you don't have great visualization skills, to see what's happening, to understand what's happening, okay? So what's happening here is you're given dimension lines that are parallel to the given axes. So I give you that dashed line in green right here. That's parallel to the z-axis. That means this line goes straight down in the z direction. Now where it lands is on this point over here that I didn't give it a name, but it's a point that's directly in this direction, which is parallel to the y-axis from the x-axis, okay? So what we can say is that point is in the xy plane, okay? And the way I know that is I'm coming off the x-axis in a line in the y direction. That's why that's in the xy plane. Okay. Now what I'm doing here is called a projection. I'm coming straight down from the end of F1 to get to that point. So I'm coming down in the z direction, straight down, and I'm landing on a point that is in the xy plane. So when I connect that point to the origin, that line is in the xy plane. So this dashed line is in the xy plane. I've got a line in the z direction landing on that. So that's a right angle in there, okay? You all with me there? Because I got a z line landing on the xy plane. That's a right angle. So what that means is I've got a right triangle there with F1. So what I can do with that is I can do cosine of 72 times 2000, and that will get me the magnitude of this force right here. So that right there is cosine 72 times whatever F1 is. Okay. Now, if you look at this sketch, you'll notice that none of the alpha, beta, or gamma are referenced directly there. There isn't an angle that's shown that connects that vector to the x, y, or z axes. notice the difference there. F2 is connected to the X, Y, and Z axes, isn't it? You see those angles there? But you don't have that for F1. What that means is you have to project it twice. So if you want to get the X component of F1, what I would do on this is I would go F1 is 2,000, okay, start with that, that's the magnitude. Now you've got to get it onto the 3 axes. Now to get it onto the first one, you go cosine of 72. That will get you into the XY plane. To get it onto the x-axis, then you're given the angle. See that projection, the cosine 72 F1 makes, was it a 41-degree angle in there with the x-axis? That's dimensioned directly. So there's your I component right there. So we good with that? We got any questions on that? Okay. So once down into the axis, then rotate it over once down into the XY plane with the 72-degree angle, then the 41-degree angle gets you onto the x-axis. Okay. All right, now there's another one for the J. Maybe I'll let you figure that one out. Okay. Yeah, it's a little bit harder, but the thing is, you're already in the XY plane. So if you can find the angle in the XY plane from cosine 72 F1 to the y-axis, you should be okay with that, okay? So you got to get that over to the y-axis. Now the last one here, see, you've got a right triangle there. You've got 72 degrees will get you from that vector, which is kind of up above the XY plane, down to the XY plane. Well, you should be able to get over to the z-axis and find gamma by doing what? If you got 72 down to the XY plane, what's the angle up to the z-axis? So you got 90 minus the 72, right? Okay. You all good with that? So, you know, and as I say, some can visualize this better than others, but there's rules to it too, and that's what I'm trying to call out for folks that have a little bit more issues visualizing things, okay? And, you know, again, kind of getting onto the professional world you're going to live in, you're going to design physical stuff. You're going to have to visualize stuff. I've built models in my office sometimes. Sometimes people think I'm a little crazy, but it helps me to see things. I mean, I'll use all sorts of ways to visualize stuff. It's important. You know, so you can get it right. So we all right with that? Okay. So you've got that, and this one, there is one angle to the z-axis, so it's just cosine gamma for the k. If you multiply the 2,000 through that expression there, you should be able to get F1. Okay. Are we all right with that? So you're going to have to figure out the J piece of that. Okay. Now the second vector there, F2, that one is a lot like the problem I just handed back. So I'll let you work through that. You know, you just need alpha, beta, and gamma. You pretty much can get the 3 of them pretty easily. You know, they're all right there. So you should be able to generate an F2 vector. Okay. So we good with that? Okay. So you should, there's the final number there on F1. You can kind of check your work. F2, I'll let you figure out. Add F1 and F2 together, you get the resultant is what you'll get. Okay, add them together, there's the resultants. You can find the square root of sum of squares and get the 2299. And then you can find the unit vector to find the angles, okay? So that's the process for that first one. So you're going to add up F1 and F2 and get FR. Take the square root of sum of the squares, you'll get the magnitude of FR. Divide the vector through by the 2299, you'll get the unit vector. And then do the inverse cosines of the unit vector to get the angles.
To find J, what do we just use? So first you want to get onto the Z and then onto the Y?
To find the J component, the first thing you got to do is get into the XY plane.
You need to find that angle between, so you have 41 degrees, it would be 90 minus 41, it gives you that other angle. And you just do the same process as for the I step, but instead you're going to use the 79, 40, or the 40, not 41, but other, 41.
Yeah, I don't know if it quite be 49, but you're going to have to do this. It's a very similar process to what you're doing here. What you're going to do is get this component first, and then swing it over to the y-axis. To do that, you have to know the angle between it and the positive y-axis, which you've got information to get. All right.
Just remember it's negative. Just like what I was talking about, negative.
We're good with that? Other questions? Okay. Okay, so you get the vectors, you add them up, you get the resultant vector, take the square root of sum of the squares to get the magnitude. To find the angles, you need the unit vector. So you divide through by the magnitude and get the unit vector. Once you have that, you can do inverse cosines to get the angles. Okay. So that's the first one there, okay? Using a double projection there, and the other one just has the angles given. Okay, the next one is 151. Do we got any questions on that? This is using position vectors, this one. Okay.
It's just like the truck example we did in class, right?
Yeah, right. And
do your A to B and your A to C, and then do stuff to that.
right, now on this one, that is something to keep in mind is, you know, if you're working on these, we do very close examples in class. Get your book out. If you have any trouble with these, just get the book out that has those templates on it. You know, we've done one. This is like the truck and the tree thing that we did in class.
Yeah.
All right, so step one is to get those coordinates. So that's a skill you're going to want to have. You're going to be able to read the coordinates. So for B, it's -453, and for C, it's 615 minus 3. Okay. So you want to get the coordinates. You're given the coordinate of A. And there is a distinct process for this. And on that handout we did in class, I laid the process out. Okay. So the first part of the process is to take RB minus RA. And that will get you the vector that goes from A to B. That's -5, -1, -1. And I always like to look at these and say, you know, does that make sense? And yeah, it looks about -5 from A to B in the X direction. It looks like you're going in the negative Y1 and you're going down 1, even though that sketch doesn't quite look that way. Do I have a bust on that? I do, don't I? Goodness.
So
Hang on here.
We want to find our FAB and FAC and then just add them together one-wise?
Yes, right. That's the big picture on this. It looks like, okay, the first one's right, that's -5. The next one's good, it's -1, but this is +1, isn't it? I got some sine errors floating around in this one. There we go, so 3 minus 2 is +1. Okay, and then this would be, and now the answers are fine, I've just got a couple little busts in here on the numbers. That should be -5 squared plus -1 squared. Not that the negative really makes any difference, because when you square it goes away, all right? And then plus 1 squared and a square root. That will still get you 5.2, but I appear to have some sine errors on that one. Okay? And how it's set up.
Divide by your magnitude and multiply it times your.
All right, so we got that. Okay, so what we did, we got a position vector. We found the magnitude of the position vector, which is the length. Okay, so this distance is 5.2 meters. Now what you want is a unit vector. A unit vector points the direction from A to B. So you can divide through by the magnitude, and that will get you a unit vector. Now a unit vector has a magnitude of 1, and it points the direction from A to B. It'll have the proper proportions to do that. So that's the next thing I want to do. I want to take that magnitude, which is 5.2, and I want to divide it through UAB. And you can see the signs are correct now, so that got corrected out. But okay, so I'm dividing the 5.2 through the vector, the -5, -1, 1. And that gets me the unit vector from A to B. So that's -0.962, -0.192, and +0.192. That vector has a magnitude of 1, and it points from A back to B. So what you can do now is scale that up by the magnitude of the force, by the 210. Okay. Okay, so now you have the unit vector. What you do is you multiply it through multiply it through by 210. That will get you a force vector that has the proper proportions now, so that it goes from A to B, but has a magnitude of 210. So you multiply the 210 through the vector. And what you get for the vector FAB is -202, -40.4, and +40.4. Okay. So that's how you use position vectors to generate a force vector.
So you don't care about the angle of the final vector? So if you add FAB and FBC, and then you don't care about the angles like the alpha and gamma?
I don't think I asked for it, no. It's not that, I might ask for it once or twice to see if you can do it, but I won't ask for it every time. Okay, it's not that important. Okay. All right, so that gets me one of the force vectors. Now you're going to have to get FAC, and then you'll add them together and get the resultant vector. Okay, so you're going to do the same thing. You're going to get FAC and then add the two vectors together and get the resultant. Okay. Questions on that? Okay. Good. All right. Okay, the next one there has a little bit of a extra thing in there. What we have is a door that's hinged on the x-axis and is angled down at 32 degrees. Okay. And what we want, and we know the force in the cable, okay, is 900 newtons. Okay, so that door is swung down from the x-axis at 32 degrees, like so. And you've got the distance from O to A, and then you've got the length of the door. It's 2.1 meters. And it's swinging down from the x-axis, so think of two hinges on the x-axis and a door there, and the door just swings down 32 degrees. Let's find the force vector from B to C. We know the magnitude is 900. Now the key to doing this is to visualize a right triangle there. AB is the hypotenuse of the right triangle. Runs right there. And then we know we have a 32-degree angle in there. So what you're going to want to do is get the components on that triangle. You're going to want to get the two legs of it. That's how you can find the coordinate of B. You need the coordinate of B to solve this one out, see? Okay. So if you go cosine of 32 times the length of the door, the 2.1, you get 1.78. Okay. So if I want that coordinate of B, I know I'm going 4.3 in the x to get to A. That's the x ordinate of B. Then I've got the 1.78 right there. That will get me the y ordinate of B. And then I'll let you find the z, okay? It's a similar thing to finding the y.
How did you solve for that 1.78?
I'm taking cosine 32 times 2.1. The door, which goes from A to B, is a hypotenuse of a right triangle. And I've got the 32-degree angle.
Oh, okay, that one.
I can just, okay? So I'm pulling that triangle out of there and using that to solve for the y distance. Okay? You good with that? Okay. All right, once you've got that, you just kind of go through that process. You want to find the position vector from B to C. So you'll have the coordinate now of B. You can find it for C. If you subtract RB from RC, you'll get that position vector that goes from B to C. Negative 4.3, negative 1.78, and 5.01. That's how you get from B to C. Take the square root of sum of the squares, you'll get the magnitude, 6.84. Divide through by the magnitude, you'll get the unit vector. Negative 0.629, negative 0.260, and 0.733. And then you scale that up by 900 and you get the force vector. Okay, so do we have any questions on that? Okay. So this thing kind of hinges on finding the coordinate of B. Once you've got that, you can then go through the position vector process to get a force vector. To get the position of B, you just have to use the right angle trig there on that triangle. Okay. I'll let you figure it out, okay? I don't know if I want to, I'm leaving that blank purposely, okay? Okay. All right. Now you've got, you can kind of see what those final answers ought to be, so you can work through that. And, and I had you meet some other people in here on purpose because I want you to work together. There's tutors available too now. We have people who can tutor statics if that's an issue too. I mean, there's lots of ways to get to this answer. I would very much encourage you to work together. I mean, that's how it goes. You got to help each other out. Okay. But I'm giving you the points you have to get to, so you can kind of check and see where you're going and if you've got a problem somewhere. Okay. All right. Questions on that one? We're doing all right? All right, why don't we we'll take a quick break here, and then we got a couple more to do, but why don't we take a break here for 5 minutes or so, and then we'll come back. So we got any questions on any of that stuff so far that we just went over? We doing all right? Totally? All right, what's up?
When you find the force vector RBC.
For the last one we were working on with the door?
Yeah.
Yeah.
So we found that vector right there.
Okay.
And it says that it's given a force of
900?
900 newtons.
Yeah.
So will we as that vector, would we multiply that by 900 newtons, then take the magnitude of that to find the force?
It says the force in cable BC is 900 newtons.
Correct.
Find the length of cable BC and the force in cable BC
Okay.
as expressed as a Cartesian vector.
Right.
So do we want to find that the Cartesian coordinates and then just multiply them times the force?
Well, what you do, you first you find the Cartesian vector for the cable is right there.
Yeah.
Cartesian means X, Y, Z.
And the newtons times that?
No, you got to make that a unit vector first. See, this is actually a length in meters here.
Okay,
It's
so
the
make
magnitude.
it a unit vector and then multiply
Yes,
the newtons?
right.
to
You
give
take
it
the
a
unit
Cartesian?
vector and multiply it by the force, and that way the resulting vector will have a magnitude of 900. See, you want to get the length of the rope out of the force vector. You don't want that in there. You just want a unit vector when you do the force. Okay. So we're good with that? Good to go? All right. Other questions? Cool. All right. That's good. All right. We good? Okay, we've also then got dot products to do. And there's two of them, and they're quite similar, and they're a little involved, these, so why don't I run through one of these with you, and I'll leave you the other one to do. So why don't I do 163, I think it is, because I've got that ready to go. Is that okay? I'll go through one of these. I think it's 163. I think. So this again, now, again, I just want to emphasize to you that these processes are a bit involved, and I know that, but and for that reason, I chart them out for you, right? So when we go through this stuff in class, this stuff is on page 211. So I'm sorry, 210 and 220. Those are the steps. So take it step by step. Okay? So if I want to find the tension and shear in that strut, the strut goes from B to C. Okay? Here's how I do that. Okay? So this is 163. All right, now I've got a force applied at B that goes from B to A. So what I want to do is I want to find the position vector from B to A. And this is what we were doing just in the previous problems. You take RA minus RB. So I switch the order of the letters. So I got RA 3 minus 4, 7, and RB minus 1, 2, 2. When I do that subtraction, I get the position vector from B to A. It's 4 minus 6, 5. Okay. Square root of sum of the squares gets me RBA. The length of that line there, that cable that goes from B to A, is 8.775 meters. Then I divide through by that, and I get a unit vector from B to A. That is a vector that points the direction from B to A. I can then scale that up by the magnitude of the force, which is 800, and I will get the force vector. So that is the process to get from 2 points, B and A in this case, and getting to a force vector that has a magnitude of 800. To get from B to A, I take A minus B. I then find the magnitude, which is the length, so square root of sum of the squares. I divide through by the magnitude and get a unit vector, and I scale it up by 800 and get a force vector.
Which one was the tension, which one's the shear?
I don't have either yet. I have the force vector. I haven't got that far yet. So I need to work with that force vector there to get the tension and the shear. Now the tension is a pull. So the tension will be going this way, pulling on B, like so, and the shear acts at right angles. So there's the tension, and here's the shear. Okay.
Is that just a rough sketch, or does that go through zero for the tension?
Does it go? It's a rough sketch. That no, there's no connection there on that going through zero. It's just the tension just goes that way. Okay.
Is the tension like a magnitude of the inverse of the pull and that kind of thing? You know what I mean? Like, I
Magnitude
want to
of.
find the tension that's going opposite of the.
Why don't we run through it? I'll show you how to do it.
Vector and then take the magnitude of that.
Well, I'll do it. I'll walk through it. Yeah. Yeah, that's fine. You know, I'm going to do all that. The other thing is, you know, maybe we'll make this stuff due Monday. Would that be a good idea? I'm getting a sense that maybe we ought to do that. We'll push this back to Monday. Will that work? You won't object? Okay. Why don't we?
We don't have school on Monday.
Oh, that's true. So that won't work. Well, we'll go Wednesday then, okay? That'll give you the weekend to work on this, so that's probably a good idea, wouldn't it? I'm just getting that sense, maybe. Okay, we'll do that. All right? Okay, so this will be due Wednesday. I'll just push it back.
22nd?
Yes. Okay. All right.
I had so much to do on Friday.
Yeah, okay. So we good? So we'll do that, okay? Now let's get through this, okay? Okay, so there you go. So there's the force. Now I had your rapt attention about 2 minutes ago, and I seem to have lost it. Now that remark did not mean. Okay, here we go. Yeah, I know. I probably should have. You're right. Here we go. Now, the next thing to do is to find a unit vector that goes from B to C. In this case, I'm going to go from C to B. Okay? Now, the reason for that is I want the tension. The tension is pulling this way, which is directed from C towards B. That's why I'm using the vector CB. That's why I could look at that and see that was going to occur. Now, what that means is when I do this dot product, I'll get a positive answer because I've already set it up to go in the proper direction. Now, had you used the vector from B to C, you'll just get a negative answer. It's no big deal. It's not a problem, okay? Okay, but I could see that tension pulls. If it pulls, it's in the direction of the green arrow. It's going from C to B. I can see that, so I'm just using my unit vector that I'm getting my position vector that way. So I go B minus C. All right, so that's 5, -4, -3. I'll take the square root of the sum of the squares, and I'll get the length of that strut there that goes from C to B, 7.071. Divide through by that, and I get a unit vector. All right. And while I'm thinking about it, I know there's so much vocabulary here. A strut is just like a shaft. It's the same thing. It's just another word for that. Don't get thrown by that word. It just means a shaft. Okay. All right. So what I've just done is I've got a unit vector from B to A, which I multiplied by 800 newtons to get a force vector, and now I have a unit vector from C to B. Once I have those things, I just take what's called a dot product, and that's how I find the projection of the force onto the line. All right. So I'm going to do a dot product. So I have those two things. I dot them together. So to dot, I multiply the like components together and I add them up. Now, if you're ever wondering how to do a dot product, it's on the formula sheet, okay? It's on the lower left-hand corner. So remember that if you're ever wanting to know how to do these mathematical operations, a dot and a cross, it's right on the formula sheet when you need it, okay? So you multiply the like components together and you add up the products. Just add them up like numbers. You get 374. See, that came out to be a positive answer. That means the force really is directed from C to B. Had you used B to C, you just would have got negative 374. And that's not a big deal. That's not a problem, okay? Okay.
Is shear always positive?
What's that?
Is shear always
Is
positive?
shear always positive? Yes.
Because I notice it seems like if you get the
Well,
negative answer, you're just going the wrong direction of shear
right.
anyways.
Yes.
So the shear is inherently
Right.
positive.
Generally speaking, in statics, when you get a negative answer, it simply means you assume the wrong direction and you just need to turn your answer, your assumption around. That's really all that means. It's not usually it's not a big deal at all. It just means turn it around. All right. Now, okay, so I got the tension. Now, if I just want to get the magnitude for the shear, which is what this problem calls for, what I realize here is I have a vector relationship. Okay, I've got the tension going that way. That's the tension. I've got the magnitude of the force going off this way at an angle, and the shear then makes a right angle with the tension. What I have there is vectors. I've got the shear and the tension are the components of the total. Okay. So if I've got two of them, I can use the theorem of Pythagoras and get the third. Here's the relationship between them. The tension and the shear are at right angles to one another. The total vector then is the hypotenuse that cuts across that relationship. If I were to rearrange that shear vector, it might be a little bit more clear what's going on here. And it's always so hard to draw on this screen. I never have enough room to put anything. But there we go. There's the total. There's the tension. The shear then is at a right angle. If I just slide it up there, maybe you can see that right angle relationship a little bit more clearly, okay? So if you have the total, which is 800, and you know the tension, you can do the theorem of Pythagoras and back into what the shear has to be, okay? So the hypotenuse squared minus one of the legs squared, if you take a square root of that, you'll get the shear. Okay?
Like the angle, can you cosine stuff to do that?
Yeah, you can just do trig to get the angle if you wanted. Yeah, sure. Once you have these things. Now there's another way to do it. And now this problem, that's all this asks for, so this problem is done. But if now the other problem, I look for vectors on that. So there's a little bit more to the other one. Are we all right with this one? Now the other one, on the other problem, I'm going to ask you to use vectors. If you're going to use vectors, you do it this way. Okay. Now the relationship with the vectors is that FBA, that force, is equal to F tension, which is one of the components, plus F shear. Okay, that's the relationship. So if I need to work with vectors, which you will need to do on 162, you have to find the tension vector. You know the tension magnitude is 374, and you know the unit direction from C to B going that way is 0.707 minus 0.566 minus 0.424. If you multiply the 374 through that, you'll get the tension vector. Okay. That's the vector. It's just taking the magnitude of the tension, which you found with the dot product, and multiplying it through the unit vector that goes from C to B. Okay. Now we know if we take the shear and the tension as vectors and add them together, we'll get the total because the shear and tension are at right angles to one another. So that relationship should hold.
that 101 negative 335, that force shared in a vector?
Yes, down below, that's a vector. So if I want to find that shear vector, I can just take the total vector from B to A and subtract off the tension. So I have the total vector from B to A. I found that earlier. I've got my tension vector here. Just do the subtraction. I'll get the shear vector right there. If I want the magnitude of that shear vector, I take the square root of sum of the squares, and I get 707. Just as I did earlier doing the theorem of Pythagoras. See, I get the same answer, just by different means. The advantage to this method here is if by chance you want vectors, you get them. And whether or not you need them might just depend on what it is you're trying to accomplish. Okay.
Since we're
Yes.
using the tension from 163, and this is 162, that would be the vectors, right?
Let's see, this is 163 here, I think. And 162, you're going to use the same method. You're going to use vectors. I mean, I didn't understand what you're asking.
No, never mind, yeah, I'm not,
So-
yeah, we're good.
Yeah, you don't need to do this on the problem I'm going through, but you need it for the integral.
Okay.
So I'm showing you the method so you know how to do it. All right. We okay with that? Now the other one then is very similar to this. It's got compression instead of tension, but that's not a big deal. That's just both axial forces, so that shouldn't be a big issue, I don't think. And I give you some of the intermediate answers there, okay? So I have intermediate check answers on page 4 for 162. And so, keep an eye on that and make sure that you're getting FAC, that's right. And look at, when you do UAB, check and make sure that that's correct. So I'll give you some intermediate answers there so you can make sure that you're on the right track. Okay? So we all right with that? Let's run through all that stuff, and that's due Wednesday now. I'll change that in Moodle. I haven't done it yet, of course, but I will. Okay? All right, good.